Well, here are the answers to the problem set on fluids in motion. The first one, blood is pumped from the heart at a rate of 5 liters per minute into the aorta, radius 1 centimeter. Determine the speed of blood through the aorta. So what's given as 5 liters per minute is actually the volume flowing in that time. And you're given the radius. So the formula for rate of flow is area of cross section times the velocity. And since you have to find the velocity, just rearrange to get Q by A. And Q is 5,000 centimeter cube by 60 seconds, because we can't use liters, and 1 liter is 1,000 centimeter cube. So that's why it's 5,000, and then a minute is 60 seconds. And then you have the area, which is pi r squared. So pi times the radius. We have both in centimeters, so that's okay. And you get 27 centimeter per second. And the second one is a similar question. You're given the radius of the artery and the flow rate is given in centimeter per second. That's actually the speed or the velocity. And you're asked to find the flow rate and also the volume that passes in a period of 30 seconds. So once you find the flow rate, which is the volume passing in 1 second, you just multiply that with 30 to get the volume that passes in 30 seconds, right? So same formula. Area is pi r squared. And this time the radius is in millimeters, so that's 0.2 centimeter. And then we're doing this also in centimeters. So you get the flow rate. Once you get the flow rate, just multiply that with 30 seconds to get the volume flowing in 30 seconds. Now the third question, you're asked to find the approximate force on a square meter of a sail given the horizontal velocity of the wind on its front surface and on its back surface. So on its front it's 6 meters per second, on the back it's 3.50 meters per second. And immediately you know this is Bernoulli's principle because the speeds are different. The density of air is given. Okay, and in fact it says this calculation based on Bernoulli's principle, and we use the modified Bernoulli's principle where you take only the pressure and kinetic energy terms because we're talking at the same height. We do not need the potential energy. So that's Bernoulli's principle. And then to find the force, you're going to have to find the difference in pressure on both sides multiplied by the area, because force is pressure times area. Correct? And now you have pressure both on the front and the back, so you take the difference in the pressure multiplied by the area. So we're looking for P1 minus P2. So from this equation, you got to make P1 minus P2 the subject, which gives 1/2 rho V2 squared minus V1 squared times A from the algebra. When you rearrange and take out 1/2 times the density and the area. Of course, the area I've multiplied, so you directly get the force. A bunch of mathematical steps, you got to be careful. So that's the density. Here are the velocities. And then the area is 1. So when you do that calculation, you get 15.3 Newton. Discuss whether this force is great enough to be effective is the B part. And the forces are small, but because the area of the sail is big, that force makes it large enough because it's acting on a large area. Now, this next question is about the lift on an aircraft, and again, it uses Bernoulli's principle. You see that the aircraft travels at 60 meters per second, so that the airspeed relative to the bottom of the wing is 60. And then you given the density, now you got to find how fast must it be moving over the upper surface. All right, so here's Bernoulli's principle again. You given, okay, so that's Bernoulli's principle, but remember you're also given that it should produce about 1000 Newton of lift per square meter. So you're given the force is 1000 and the area. So multiply the force with the area, you get the pressure difference times area, like in the last problem. So P1 minus P2, again as before, make that the subject. And because we are asked to calculate velocity 2, we make that the subject. Got to be careful there, you got to take the square root. That's why I've raised it to half. Substitute the numbers and you get the speed. Now P1 minus P2 is 1000 newtons because one of the pressures is 0. So the difference is just equal to the pressure you need. And the B part says how fast must air move over the upper surface at a cruising speed. So when it's cruising at 245 meters per second, you got to rework this problem again. And there the air density is only 1/4 that at the sea level. So you got to find that. Oh, okay. So now I divided the density by 4. Thought I had missed that, but I actually did it and I forgot to write that. Now I did. So you see I've taken the density as 1/4 of the previous one. So same thing, but now the air has to be moving at 257 meters per second. I hope that makes sense. Now we got to take this question a little bit slower because it says the left ventricle of a resting adult's heart pumps blood at a flow rate. So that's the flow rate, that is Q of 83 centimeter cube per second, and increasing its pressure by 110 millimeters of mercury, its speed from 0 to 30 centimeter per second, and its height by 5 centimeter. So when the heart pumps blood at that flow rate, it's increasing the pressure, number one, it's increasing the speed, and also increasing the height. All right, so you see that it's giving it pressure energy, kinetic energy, and potential energy. And you got to find the total power output. So you got to find the total power that the heart is expending. Now, since all three types of energy are here, you got to use the entire Bernoulli's principle. And I started out with directly with power as energy multiplied by Q. Because energy per second is power, right? Energy per second is power. This whole thing gives you the energy one, and then you have Q, which is volume flowing per second. And so this is the formula to find power. So technically this comes out to be the pressure times volume by time. So that's how you find the power. The pressure is given in 110 millimeter mercury, which we need to convert into pascals by using the idea that 133 pascals is 1 millimeter mercury. So we get the pressure in the proper units, Newton per meter squared or Pascal. And then you got to find 1/2 rho velocity squared, That's the density of blood, and then you have the speed. 30 centimeter per second should be changed into meter per second. That's why it's 0.3, which gives you 47.25. Look at the unit. It's consistent, right? All three terms must have the same units because you're adding them. They must have the same units. Otherwise, you can't add. So now the third one, the density times G, which is 9.80, times the height, again is in centimeters, so I changed into meter. So once you get those three quantities, just add them up and multiply with the flow rate. But the flow rate should be in meter cube per second. Got to be careful. So that's all those three terms added up, and then 83 centimeter cube per second times 10 to the negative 6. Because 1 meter cube is a million centimeter cube, okay? So that's why. And then when you do that, you get the power as 1.26 watts. So that's how you do that. Wonderful question. You technically don't need the other questions, so I am skipping to number 10, which is the last question. And this question says, when physicians diagnose arterial blockages, they quote the reduction in flow rate. If the flow rate in an artery has been reduced to 10% of its normal value by a blood clot, and the average pressure difference is increased by 20%, by what factor has the clot reduced the radius of the artery? Here you got to use Puschel's formula, which I've given you. The flow rate is given by the difference in pressure, pi r raised to 4 by 8 eta times the length. So r is the radius of the artery. P1 and P2 are the pressures at the two ends of the artery. Of course, the pressure at one end, where it's connected to the heart, is going to be higher. So you have that. And then eta, this funny symbol here, eta is the viscosity. And then you have the length. So nothing is mentioned about the length of the artery. You don't have, you only have the pressure and the radius. So look at what I'm doing. I'm making the radius the subject there. And I made the radius the subject, and I put P2 minus P1. I just wrote it as delta P. It's the same thing. I rearranged it. But this has to be raised to the power 4 because r raised to 4 is there. And I put r prime, q prime, and delta prime to show the three quantities that changed. Right? So the radius has changed, therefore the flow rate has changed, and the pressure has changed. So the viscosity and length are the same, right? So this whole thing should be raised to 1 by 4, which I will write in a second. Because you have to take the fourth root. There it is. You have to take the fourth root to get the radius because it's raised to 4. And then plug in the given terms. Now, let me tell you what I did. You know, the quantities that did not change will just get cancelled. The 8 and the pi, you know, all those will get cancelled. So the only quantities that are given are 10% reduction in the flow rate. So that's why the new one is 0.1 Q, because 10% is 0.1. And then it says the pressure difference increased by 20, so it's 1.2 now, right? Takes a little courage to understand that. So every other quantity got cancelled, and I just need this ratio, and I get it as 0.537 times the radius. So the radius is reduced to 53.7% of the original, or the normal value. Well, I did this quickly, but I hope all of this makes sense. Maybe you got to go over it again. But thank you and good luck.